Okay, so I'm very happy to introduce Matias Delgadino, who I met just a few weeks ago at Austin. He will talk about generative adversarial networks, dynamics and mode collapse. So please.
All right. Thank you. Thank you for the invitation and the opportunity to talk a bit. Yeah, so I guess I'll be talking about like sort of what are the kind of what are the type of things that we can say from like some evolutionary PDEs in terms of trying to understand some of these machine learning algorithms. So generative adversarial networks, now it's a little bit outdated in a sense, but we're mathematicians, we're always like 10 years late to the party. This is, I guess, 5 years late to the party. There was this first algorithm that actually was able to generate realistic looking images. Okay, so I guess, let's see if this kind of works. So we open Safari. So you actually just grab like this person doesn't exist. And so whatever you upload the picture, there's another different person just didn't exist. And so the algorithm is just actually creating the pictures of these people that don't exist from having just data that was before. Okay, so so what is the starting point? So the starting point is that you have 200,000 samples of pictures of people, and you can just like open the link, and there's like a lot of data of pictures that kind of look like this. Okay, and these are celebrities that were taking like some high resolution pictures, and so this is your initial. This is how you start, and then you want to replicate some other samples that are not within the guys that you've already seen that look realistic. Okay, and so yeah, so what just if you've never seen kind of how like these guys come up, so you have that. An image is coming from like 3 different channels, like red, green, and blue. And so you have basically a matrix, which is depending the size of the matrix, it depends on the resolution of your picture. And in each one of the pixels, you have the intensity of the red color, of the green color, and the blue color. Okay, and if you add them up, what you're going to see is the picture. Okay, so basically what we have is we have samples from so from I equals to 1 to 200,000 of elements that are in this case, 1,024 times 1,024 times 3, which is the 3 channels, red, green, and blue. Okay, so the RGB. So if you, of course, if you're looking at kind of a somewhat realistic and in fact a little outdated nowadays type of problem, you have something that has 3 million dimensions. Okay, so we're looking at a high dimensional problem. And we're trying to understand how we create a sample in R to the 3 millions, okay? Just giving a new sample, given that you have already a lot of information, okay? A lot of information can be arguable, but of course, this is when we are going to start making assumptions. So the idea is that we're going to assume that we have access to infinite data samples. And we are going to even more assume that all of these data samples are identically distributed. And in the background, what we have is an underlying probability distribution P star, okay, which is this probability on this R to the K, where K is a large number, okay? So it's much, much, much larger than 1. All right, so this is, in essence, kind of the underlying thing. And so we want to be able to sample P star just from the fact that we have access to other samples. Okay, so we want to sample P star synthetically. That would be the idea. So the other assumption which is made, and in fact, I've never seen this written in a kind of mathematically correct way. This is in the background of what the algorithm is doing, is that you're going to be assuming that effectively the dimension is not as large as the space that you're dealing with, okay? So you're dealing with 3 million dimensions, but effectively the dimension of the support should be condensed into some lower dimensional manifold, where L is actually much smaller than 3 million, okay? So in fact, in this problem particularly, I think they even take L to be 128, okay? So you have some really small L compared to what K is, because you're going to be able to need to do computations. So you are going to be able, you are going to need to take some L which is much smaller. Of course, you could take L sort of equal to 1, but that doesn't make sense. I mean, in a sense, you expect that the pictures of faces would actually have some degrees of dependence. And I mean, probably it's not 3 million, but it should be something large enough, okay? So if we want to make this kind of, more than assumption, this kind of guiding principle more precise, what we're going to consider, at least in these generative adversarial networks, is we're going to consider some prior distribution, which is I'm going to consider as a random variable Z, which is just a normal variable. It's the probability on RL, where RL in general, this is my latent space, okay? So I'm going to have some Z, and I want to transform this sort of normal random variable into some picture, okay? So what we're going to consider is some continuous function G that is mapping RL into RK, which from now on we're going to call the generator. And what we are going to be considering at the level of the space of pictures is we're going to be considering the random variable given by G evaluating in Z, which is distributed in terms of notation by this G push forward N, okay, which is now a probability in RK. Okay, so what is the objective? Okay, I would not even claim that this is a full-fledged problem yet. Is I want to find some G, some generator, which is easy to evaluate, such that whenever I take some distance between the distribution of G push forward and N and P star, that this is small, okay? And this is small for some meaningful metric D on the probabilities of RK. Okay, so small enough. Of course, I mean, I don't expect this to be exactly 0, but I want something that at least is close to indistinguishable from G's push forward N and P star. Okay, and so then the question is, what is the metric? At least if you read some of these machine learning papers, one of the things I found like a little like astonishing is that, you know, the actual metric that these papers are using is actually the real eyeball metric, in the sense that they actually hire people in sort of low wages countries, and they will say, okay, well, you label my data. Okay, so is this picture look real to you or not? Okay, and so the eyeball metric is the one that rules them all. Okay, so this is the metric that papers will compare themselves with. Okay, they'll send their like produce images to some workers online, and they will actually label them for like sends a picture or whatever. And that's how you actually kind of check these things. The other thing, I mean, of course, we're not going to use the eyeball metric, and in fact, this is not how you use the algorithm, but that's the actual one that you actually, that's your actual objective, okay? So that's the applied objective that we care about here. So what we are going to consider eventually is that we're going to consider G to be some parametric function. So it's going to depend on some parameters theta. And what I'm going to be doing is trying to infimize the distance of G theta, push forward the normal distance with P star, okay? The only catch is also that we do not have access to the distribution P star in sort of some functional way. We only have access to samples, okay? So whenever we give a notion of D, we are only going to be able to evaluate it in samples, okay? So we need to have some metric D that can be evaluated with respect of samples. Okay, so the first original like generative adversarial network algorithm, so what they were considering was the relative entropy, okay? So what is the surprise that you can find G push forward N, knowing that you have P star as your background, okay? And so, okay, so just as a reminder, so this is the expectation of the Radon-Nikodym derivative of the function x log x applied to the Radon-Nikodym derivative. And there is a bit of a thing here is that if G push forward N is not absolutely continuous with respect to P star, this is equal to plus infinity, okay? And this is something that kind of was observed in general, is that this is fairly degenerate in the sense that if your G push forward N does not actually align with P star, then there's little you're going to be learning from this to begin with, okay? Then the next comment is that we actually need to evaluate it in samples, okay? So we don't have access to D, G push forward, and P star, and so we need to write some way of actually just using samples to get some idea of what the relative entropy is. Okay, and so what these guys realized, okay, and I put the reference here, which is Goodfellow and some collaborators. So what they did was to consider the Legendre-Fenchel transform of the relative entropy, okay? And in fact, they used the symmetric version of this, but I think for the purpose of this talk, this doesn't really matter. So the relative entropy can be written in a dual form in terms of the supremum of sort of the dual of measures, just the continuous and bounded functions in RK. And what I'm going to be considering is F composed with G evaluated at D and Z, which is something minus the logarithm of E to the, okay, and there is a typo here, this should be F. Okay, and so F here is going to be called the discriminator. And so morally, what F is going to try to exploit is actually going to kind of exploit when I see some relative difference between G push forward and P star, okay? So this F is always going to try to like maximize this quantity here. So the advantage is whenever we fix the discriminator F, we can actually sample the integrals. Of course, there is a supremum here, okay, that we need to take care of eventually. But at the beginning, we can say, okay, so if we fix the discriminator, we can sample these integrals, okay? So what does this mean is that we can take a batch of data. So we can take Z1 through Zm, which is distributed with respect to this normal distribution. And then we can take X1 through Xm, which are distributed by the real data P star. And so then the integrals with respect of D and Z and D P star can be approximated. They can be approximated by this sort of empirical sum here. Okay, so usually the batch size is a sort of hyperparameter that you need to tune. At least for simplicity in this talk, we are going to start thinking that, okay, so that's M, that M is equal to 1. So I'm just taking a single sort of sample and I'm trying to approximate this at each time. So the point is that I'm going to do this over and over again and so many times that every kind of variation is going to actually cancel out in the limit. Okay, so in a law of large numbers, everything that is like the difference between the expectation and the sampling that I'm taking is going to disappear in the limits. Okay, all right, and so this goes back to the comment that I was doing earlier, so that if you do not know that G push forward N is absolutely continuous with respect to P star, then what we're going to have is that the relative entropy between G push forward N and P star is going to be equal to plus infinity. So there's nothing to be learned from that. Okay, so once I have that, you know, okay, so if I have here, so I'm the support of P star, and then I have here, okay, something that looks similar, close enough, the support of G push forward N. It doesn't really matter how close this guy is. It doesn't matter how close this guy is. I'm learning nothing in a sense. So the relative entropy is plus infinity, and these guys are as different as they could be. But of course, we're assuming that this guy behaves like some sort of manifold. So we are thinking, okay, and we are assuming that this guy behaves like some manifold of dimension L. So it's hard to imagine that like from the start you're going to get some G push forward N, which is going to be well aligned. Okay. So yeah, so the idea is that we will learn nothing if the distributions are not aligned from the start. So the alternative and the notion of like this Wasserstein generative adversarial network, and this was done by the paper that I'm citing here, Abjosky, Chintala, and Butu. They were like, okay, well, this is too singular. What if we consider a slightly weaker metric? And what they consider is the one Wasserstein distance. And the way that we're going to evaluate it with samples, so the one Wasserstein distance is just going to be the minimum. Yeah, okay, I'm missing a minimum here. So I'm missing a minimum over all the possible couplings between x and z of the distance, the Euclidean distance between x minus g of z. Of course, you could always ask, why are you taking the Euclidean distance? Why is this meaningful with respect to pictures? And again, so the answer in these kind of things are like, well, of course, these are all validated with the eyeball metric at the end of the day. So, you know, if it works, it works. If it doesn't work, you know, you throw it away. Okay, so and Kantorovich duality is basically saying that so you can write this minimization with respect of the coupling as a supremum with respect of now a discriminator where the discriminator is bounded has a bounded Lipschitz norm 1. And I can take the same kind of discriminator here. I have no nonlinearity in some sense. So I have to evaluate f composed with g integrated with the nz minus f integrated with the p star. Okay. And again, this guy can be sampled. So I can just sample x. I can just sample x and sample z and get some estimator of this quantity for every fixed f. Of course, this doesn't take care of the supremum, and that's kind of what we're going to look next. Okay, so what do I want to do? I want to use this expression to try to come up with a way of creating some better functions for G. Okay, just a comment that I've been making is the advantage of the one Wasserstein distance is that this guy does not degenerate, and because it does not degenerate, you expect that it's going to behave a little better than the relative entropy, that it's going to be less picky when you're trying to learn from the beginning, and it's not going to depend too much on your initial conditions, and it's going to converge more often than the original GAN. So, okay, so now the point is that you know, we only have some finite capacity. So the capacity of like computing, we need to fit in some particular parametric form of the generator and the discriminator, and we want to try to understand how are we going to find the optimal parameter θ1 through θn to get the best answer possible. Okay, so. So here I'm just saying I'm considering the case of the simplest case in which you have one hidden layer neural network. So I have some nonlinearity, but I'm not stacking the nonlinearities up. Okay, so there's a stacking of nonlinearities in the sense that, you know, you're going to have f composed with g, but each one of them in a sense is depending on a single nonlinearity, which is going to be this activation function sigma. And the idea is that these are already a broad enough class to be able to approximate any continuous function. And the advantage of using these type of networks is that you can use the fact that the labeling of these parameters don't actually matter. And so I can use that instead of looking at the evolution in terms of the parameters themselves, I can look at the density of parameters and what is the evolution of the density of parameters. Okay, and that's kind of where I want to get at. So if you've never seen these things before, let's kind of look at sort of a specific example. So this the typical example, smooth example would be the sigmoid. So the sigmoid is just the function 1 plus e to the minus t. And now the idea is that, okay, so the generator needs to be something that is coming from RL and going into RK. Okay, so I need to have a vector of each one of them, and I'm just going to repeat it, but my vector θi is going to have components with respect of each in each dimension k, okay? And this is, in fact, a high-dimensional guy because, I mean, at the end of the day, we're going to have r to the 2 plus l times k, okay? So it's actually fairly high-dimensional. And similarly, for the discriminator, I need something that takes as an input x, which is in rk, and gives me a function back r, okay? And here the parameters are exactly these omega j's are going to be alpha j, beta j, and gamma j. And the idea is that I'm taking an average, okay, so some sort of mean field scaling of sigma of x omega j. Okay. So the main kind of point with this network is that the relative order of the parameters does not affect the output function. Okay, so instead of looking at the evolution of the whole parameters, I can consider without losing any information to what happens if with respect to the empirical function. Okay, so what I'm saying is if I take theta I and theta j, and if I change the relative position, the function that I'm getting doesn't change. So instead of looking at the actual values of these points specifically, what I can look is at the associated empirical measure. Okay, and now this empirical measure is something that does not change in the space where when I take n larger and larger, this doesn't actually change. Okay, and the advantage is I can take a limit when n goes to infinity and find some actual limit in these probabilities of R, RL, R to the k. Okay, so this, if you've seen probably some pictures of this before. So morally, you have some input. Here you would have sort of n pieces. And so the input goes to each one of these guys. And then here we have, so we have input and we have output. And the idea is that we are just connecting these guys completely. Now, so this is the case if we have a single neural layer neural network, but of course you can start thinking of what happens when I have more than one layer. And the idea is now that the parameters with respect of this layer are exchangeable, but the parameters with respect of this layer are exchangeable. Okay, so the more layers I'm having, the more probability distributions that I'm going to have to keep track of and try to understand how this guy, the pink guy, is going to have an evolution, and then the evolution of the pink guy is going to change the evolution of the orange thing. Okay, so similarly, I'm saying the same thing about the parameters omega 1 through omega n. I'm going to encode this into some new m, where new m is just this empirical measure of 1 over n sum from I equals to 1 to m. And okay, I'm not going to make much of a fuss about it. In fact, you can think that n and m are the same, but there is no need that you have the same network for the generator and the discriminator. So you could think that the discriminator is something that is much stronger and is able to discern things better than how much the generator is doing. Okay, in general, at least in applications that I've seen or like in the comments that people say, that this works best if you have that the generator and the discriminator are working more or less at the same, nobody is actually winning, okay? So that you actually have some sort of fair competition between these guys. So you want to have that the architecture for the generator and the discriminator are more or less on par with each other. All right, so let's go to the actual algorithm. Okay, so the point that I'm going to try to make in this talk is that you can think of the algorithm as discretization of a PDE. Okay, so you have some background PDE, and what this is actually doing is discretizing the PDE. And so if you look at the level of the evolution of the parameters at the evolution of mu n and mu m, in essence, what this is doing is discretizing a PDE. Okay, so we are going to have a lot of parameters that we'll try to go through some of them. So alpha is going to be your learning rate. So in a sense, this is, if you consider of a sort of fictitious time, this would be some like delta t. C is going to be some clipping parameter that has to do with enforcing the Lipschitz 1 condition. M is the batch size. We are considering 1 for this talk. It doesn't really matter. And then there is a comment here, which is the critics. So the point is that we're going to be thinking that we want to take the supremum. All right, let's go back. So we want to take the supremum over the discriminator, okay? So we should be taking the best possible discriminator at each given point if I want to be approximating the D1 distance. So one of the ways that people have been looking at this is by giving some sort of advantage to the discriminator by means of training it more, okay? So making more steps in terms of the update of the critic versus of the discriminator versus the updates of the generator, okay? So the algorithm is going to be fairly simple. I mean, we're going to simplify it a bit more, but so the idea is you're going to initialize your parameters, and while your generator parameters has not converged, which you have to figure out how you're going to consider that they have converged, you're going to sample the real data. You're going to take a gradient with respect of the parameters on the sampled version of your discriminator of your approximation of your Wasserstein 1 distance, and you're going to update your parameters using this RMS prop, which is something similar to stochastic gradient descent. Okay, and I'll tell a bit more about it. Okay, and this idea is that you do an inner loop on n-critic, which is this is the advantage that the critic has with respect of the discriminator. Okay, so you're going to train the critic more than the discriminator, and then after you've done n evaluations of this guy, you're going to evaluate once the update step for the generator. Okay. And again, you're sampling and just updating what happens with the generator. Okay, so learning rate in this case is some super small number. What I'm going to be considering is some sort of fictitious, this as a fictitious time discretization in which delta t is of the form alpha divided by n. Okay, and the idea that you have a divided by n has to do with this mean field scaling that I put on the neural networks. If you take out the mean field scaling, the neural networks, then you just got alpha. NC, which is in this case equals to 5, is going to be the critic's advantage. And in fact, did I still have a typo here? So what we're going to consider is some gamma C, which is basically a time rescaling of how fast I'm evolving in the critic's evolution equation compared to how fast I'm evolving in the generator equation, okay? So N is associated to the generator and M is associated to the discriminator. And now I'm trying to think that I feel like this NC should be upstairs, but you know, the idea is that the larger the NC is, the critics has a bigger advantage. So it means that it's actually evolving faster than the discriminator, okay? And we'll see this in the PDE. Okay, and the clipping parameter, this C, which is 0.01, is just enforcing that at each step, I can actually say that the weights omega I in L infinity are less or equal than this constant C. Okay, and this is to satisfy a uniform Lipschitz bound. Okay, so whenever I try to get out of the box of size 0.01, I'm going to be pushed back in. Okay, so that's just the way it is that you evolve. You take a discrete timing step. You take a discrete step, and then if you left the box, you're going to be pushed back inside. And okay, we'll see how that affects the PDE that you're going to be getting. All right, and just one last thing. So one of the things that I was mentioning in the algorithm is this RMS prop. So RMS prop is a version of stochastic gradient descent that normalizes the gradient. And I think the concept of this is that you are trying to escape plateaus. Okay, so if you have not converged to a minimizer or a local minimizer at least, you want to be able to escape this guy here. And so morally what you're doing is you take a running average, you take a running discounted average of the square size of the gradient with respect of a given parameter theta I, okay? And when you take the update step on theta k plus 1, instead of taking the update step as just some alpha times the value of the derivative, what you should be getting is some normalizing factor, which takes into consideration the size of the gradients up to this point, okay? For the purpose of this talk, we are going to avoid the technicalities that this bring, and we're just going to consider an SGD in which this MK is equal to 1 for every k. Okay, so I'm just not going to, I'm going to ignore the normalization. Okay, so if I take beta equals to 1 here, the point would be that I'm just taking the sign of in which direction is this pointing for each parameter. Okay, so just to kind of fix the ideas of where this is coming from, we can think of a slightly simpler problem. We are considering supervised learning. So supervised learning, I want to minimize over my parameters theta, some energy with respect of theta. So I want to minimize over theta. So this generator function theta of x with respect of some g star of x. So I want to minimize the L2 distance, where p star here is the data distribution. Okay, so I have some data distribution, and here I have some labeling, and I'm trying to minimize what is the L2 error that I'm making between my generated samples and the labeling that I'm getting. So the way that we can think of this is that, we are minimizing some in theta, some function e, some little e, that is evaluated at theta and x with respect of dp star x. Okay, so what is the algorithm of SGD? So the algorithm for SGD is, while the parameters have not converged, I sample xk from p star. Okay, so this would be if I take in a batch size of 1. So the m in the algorithm is 1. So, and I'm going to update my parameters by saying that theta k plus 1 is going to be equal to theta k minus alpha. And then I take the theta derivative of e evaluated at theta k and xk. Okay. And I do this a lot of times. Okay, so the point is that you're going to do this so many times that the errors that you're going to be doing from sampling are going to average out. Okay, and so the idea is that this SGD is a stochastic discretization of gradient descent. Okay, so if I want to compute gradient descent, so if I want to take the time derivative of theta tilde minus the gradient of this guy, so if I don't have access to the full p star, but I only have access to samples, so instead of doing forward Euler, so the idea is that I would like, for instance, to do forward Euler. I cannot do forward Euler because I'm not able to evaluate this completely, but at least I'm able to evaluate it if I'm given a finite number of samples. So I evaluate it in a stochastic way, and so I do some stochastic sort of forward Euler. And the idea is that the dynamics of this guy are in fact converging to this with a different scaling with respect of the time discretization. All right, so okay, what I'm going to be using is the exchangeability again. So what is g theta of x? G theta of x is just this 1 over n, the sum from I equals to 1 of sigma of x evaluated at theta I. So if I fix my x, I can think of this as the dual product between g of x evaluated with the second variable integrating with respect of mu n, where this is my empirical distribution. So, okay, the point is that we are going to use the exchangeability, so we can actually realize that, what we care about is what happens for each theta I. Okay, so for each theta I, so if I take the derivative with respect of theta I, what I'm actually going to be getting is 1 over n, some velocity field that depends on mu n. Okay, so it depends on all of the particles at the same time, but it depends only on with respect of the empirical distribution evaluated at theta I. Okay, and the idea is that this is here independent of I. Okay, and this is the whole point, that this is exchangeable. So we have a solution to the dynamics theta dot of t is equal to minus the gradient of E of theta of t. If and only if what we have is that the empirical measure is satisfying a continuity equation. Okay, so it's equivalent to say that these parameters are satisfying the gradient descent. Is equivalent to saying that my empirical measure is satisfying. This is called like so this is satisfying this continuity equation where the velocity field is coming here, and because I took the mean field scaling, I have a 1 over n in front here. Okay, so I need to be careful that when I'm discretizing this guy, I'm rescaling time in the right way so that I don't actually get a trivial dynamic in the limit. So I need to rescale time in such a way that I get rid of the 1 over n, and that's why I was taking delta t to be of the form alpha divided by n. Okay, so this is the theorem is a sort of law of large numbers, and this was done by sort of many groups approximately at the same size, some of them slightly later, but they kind of realized the same thing. So you can exploit this exchangeability to say that if my initial conditions were sampled from some initial distribution, then mu n, which is a stochastic measure valued random variable, is going to converge to a deterministic process, which concentrates in the unique solution of the continuity equation. Okay. Okay, and here there is an up to a time rescaling. Okay, so up to a sort of n rescaling, what we actually are going to obtain is that you are actually satisfying this PDE. Okay, and that's the whole point, is that in essence, what the stochastic gradient descent algorithm that I wrote here is a discretization of the PDE. All right, so. All right, and in fact, you can even have a gradient flow interpretation. So considering the energy E, which is going from the probabilities of R, so I can replace theta by the appropriate measure. And so this is E, which is evaluated in mu instead of theta. And so what SGD is the 2 gradient flow of E, okay? And in fact, if you expand the square, you can actually obtain that this is an aggregation equation, okay? So this is a sort of clean aggregation equation, and you can see it here. So G of mu is linear in mu, and then I'm taking a square, okay? So what I should be getting is something that is square respect to mu. So if you kind of open up the square and then you reconfigure things, what you're going to be obtaining is that I get some interaction potential, this W evaluated at the parameters, and then I have some potential V as well. Okay, so this is not the same V as before. That's, I guess, bad notation plus some constant here. Okay, and you can write down W and V explicitly, and what you are going to be getting as the limit of HGD is a nonlinear continuity equation where the velocity field depends on the measure itself, and it depends through these interactions here. Okay, and this is the nonlinearity. And now you could start asking what happens when t goes to infinity. And in fact, that's even, like, I would claim an open question. How much can we say about the time when t goes to infinity? And especially if you add a tiny bit of noise coming from SGD or some other sort of discretization, can we actually claim that this will be converging to some unique minimizer to this problem? Okay, so there is it happens to be a unique minimizer because this guy is linearly convex.
Sorry, Matias, can you remind us what's the relation between theta 1 and theta 2 and mu?
Yeah, so these are dummy variables.
Oh, these are there is mu there. Okay, sorry, I missed it. Yeah.
Does that make sense now? Cool. Yeah, so these are just dummy variables of integration. So these, I mean, I don't know, typically this would be like, you know, x minus y, d mu of x, d mu of y. So this should be theta prime, or whatever you want to call it.
Yeah, thank you.
Sure. All right, so going back to the VAPS58 GAN. So if I kind of simplify and I replace RMS prop by SGD, and I take this one layer neural network, of course, I mean, the more assumptions I'm taking, the farther and farther away I'm taking from this guy. But the idea is I want to understand the dynamics. Okay, what's happening at the level of the dynamics? What's happening in the limit when I take this over parameterized limit when n and m are going to infinity? Okay, and so the idea of what is happening is, okay, I'm having, in a sense, I have some like discretization of the PDE or the ODE, depends on how you want to see it, in which what we're going to have is that the update of theta k of theta is going to be theta k plus some delta t, some velocity field that is on theta, which is depending on nu n and mu n, and is evaluated at these xk, zk, which are going to be sampled from p star and n respectively. Okay, and the W of j of k plus 1 is basically the same thing, but the extra thing is because I'm clipping, okay, the clipping is the projection onto the space minus c, comma c to the 1 L plus 1. Okay, so this projection is to enforce the Lipschitz condition. Okay, and I'm even taking another simplification here, which has to do with this gamma C here, which has to do with the relative speed that I am training the critic versus how much training the generator. And this basically is giving me a speed up. Okay, so how fast this guy is with respect to the previous one. Okay, so the larger this gamma is, the faster I'm training. Okay, so the faster like WJ is going to be converging to something, or at least that's what I would hope. So if you look at the associated PDE, the associated PDE is going to be a gradient flow. Okay, so what we're going to have is some sort of, I mean, saddle point would be to say, so I have some energy now that is depending on mu and nu, which are these parameter distributions. And okay, so similar to what I was doing before in the supervised learning case, now I have something that is depending on now on two measures, this f of nu evaluated at g of mu of z, d and z, minus f of nu of x, dp star of x, okay? Now, I'm going to take, if I take the derivative of this measure, of this function that takes measures, I'm taking this derivative with respect of the measure mu in the sense of the Wasserstein 2. I actually get a dynamic that, I mean, this is similar to SGD. So this would be the same as just gradient descent or like just taking a gradient flow. But now with respect of nu, what I'm going to be getting is a little bit more complicated because I have this projection of pi q here. Okay, and what is one of the points of this projection of pi q? Projection of pi q is actually a discontinuous operator. Okay, so it's going to make a big difference. It's going to be a big difference. Okay, so if this is my q, if I'm inside, the particle can do whatever it wants. But if I'm at the boundary, and this is my vector field, this guy here is going to get projected onto this guy here. Okay, so what I'm trying to say is that once I go to the boundary, I'm not going to allow anything to leave. Okay, so I'm just going to project it. Okay, so if I'm super, super close to here and I look at some point which is right next to it, this is the vector. But eventually, when I hit the boundary, the component that is pushing outwards is going to disappear. Okay, so this is discontinuous. Okay, which makes a bit of a problem, but again, because we're dealing with a convex set, this is how you deal with it. Okay, so it's this discontinuous, but it's discontinuous in a way that is actually contracting. Okay, so yeah, so the first thing, so we have the PDE, and this is joint work with René Cabrera, which is a postdoc here, and Bruno Suazura, which is a student at PUC in Rio de Janeiro. And the idea is that we can show that this PDE has a unique stable solution, and you need to be a little careful on kind of the Lipschitz dependence of your velocity field with respect of your parameters, and this grows with respect to your parameters, so you're not going to be able to get a clean D2 to D2, and so you have to have a slightly higher Wasserstein space at your initial condition to control the D2 distance, okay? And I'm saying for any t between 0 t, I have some constant that gives me this, and this c behaves like e to the t kind of thing, okay? So it grows exponentially, okay? So it's not a good constant in any way, but it's just more about saying, okay, well, I have some problem that actually makes sense. All right, and now once we have this kind of notion of this unique stable solution, then one of the observations is, and one of the main observations kind of I didn't realize when I was looking at this thing, but it makes complete sense once kind of you think about it for a second, is that let's say that we have some initial distribution, new initial, okay? And you have this vector field that is pushing you to the left. Okay, so this is at t equals to 0. So what happens at a bigger t, the support of this new initial can actually become singular. Okay, so once it hits the boundary, it's like a pigeon. Okay, it's gonna hit the boundary and it's gonna get like flattened against it. Okay, and it's just gonna get stuck into the boundary. Okay, and even though f can later start pointing inwards, okay, so the velocity field start pointing inwards, this guy is never going to decorrelate, and it's going to keep some sort of lower dimensional thing, okay? So in fact, if I push everything to this point here in the corner, so once it got like pinned into a corner, it's going to become a delta, and it's going to be a delta for all times. Okay, so that's one of the things that we can tell. I mean, in a sense, like, because we have sort of the notion of measure valued solutions, it doesn't, I mean, this is not blow up. Okay, so this is not blow up in terms of like Keller-Segal or anything like that. So it can coagulate it to a single point in finite time, and it will stay a delta at omega t for all t bigger than after the coagulation point. Okay, so this PDE admits solutions like this. And that already tells you that that's why this is a little finicky, because depending on your initial condition, it could be that all of a sudden your particles, like all your discriminator gets stuck in a point in the boundary. And then it's never going to be able to kind of decorrelate to become something wider and become something nicer. All right. Yeah, so what is the theorem? So the theorem is that if you take sort of the WGAN algorithm, the HDD version of the WGAN algorithm, what you're going to be able to say is that in expectation, the Wasserstein-2 distance between mu n of t, and the solution to the mean field problem is going to behave like C divided by n, okay? So the larger the n is going to be, the closer these two problems are going to be. Of course, this C is horrible in time, and so should be thinking of just a fixed time interval. And one of the things also is like there is a bit of a catch here, because my mu infinity and my nu infinity are also still discrete, okay? I'm not thinking that I'm taking sampling from an initial distribution. I mean, when I'm taking mu infinity and nu infinity, I'm coupling them with the fact that I have the same initial condition that I've had for the algorithm, okay? Because if I don't couple the initial conditions, I suffer the curse of dimensionality, okay? So if we start sampling theta I and omega j, and then we have this sample from this mu bar initial and nu bar initial, then you can say the same thing about the Wasserstein distance, but now your factor here becomes awful. Okay, and this starts depending on the curse of dimensionality, and I really have to have a really high end to say that these guys are close. Okay, so the difference is what is the initial condition for this mu bar infinity. So here, this mu infinity is coupled, the initial condition is coupled with the initial condition of mu n, okay? So if I don't couple the initial conditions, I cannot expect to have a C divided by n, okay? In fact, it's just, if you take the Wasserstein distance in high dimensions and you sample it, you're going to have something that is depending on dimension. Okay, so, I mean, I don't really have much time. So at the background of the proof, if you've never seen like, the idea is that, okay, so instead of taking, so I'm thinking of trying to do theta dot is equal to B of theta, which is equal to some expectation of some little b of theta x, okay? So instead of, so if I try to do forward Euler, would be like this bottom step here. And now if I do some sort of stochastic version of forward Euler, I'm just sampling x, and I'm trying to see what happens when I do this over and over again. And the idea is that you just write the difference. And if you knew that V was Lipschitz, you can actually say that the expectation of the error squared is going to behave like C times delta T. Okay, and this is assuming that this is Lipschitz, and this is the same type of computations as you show for the law of large numbers. All right, yeah, I'm running out of time. So, all right, so what are the problems and what are kind of the things that we can say from the PDE, or at least from the dynamics, this kind of thing? So there are some no problems of GAN. So one of them is mode collapse. So you start trying to generate all the handwritten digits from 0 to 9. And the point is that eventually your generative adversarial network just starts filling once, okay? And this has to do a bit with the concept of the relative entropy, the fact that, you know, if you are, you're a little conservative in terms of like trying to exit the domain of the support of this guy. So if not, you're going to have an infinity gradient. So you're not really rewarding like being explorative in some sense, okay? So at some point you get ones, And this is actually something pretty funny. So ChatGPT apparently does a similar thing. And apparently I put my abstract on ChatGPT. And so ChatGPT has the wrong correlation of words, and it uses the word delve a lot, okay? And so if you put something on ChatGPT, just worry that it might have delve on it. And in fact, I submitted this abstract, just wrote 3 lines, put it on ChatGPT, see what it came out, and then it looked reasonable. But yeah, of course, if you look at it too closely, there is a delve there, which, you know, it's not really used as much in the English language. Anyway, so what is the dynamics are going to be able to try to understand what is this sort of failure to converge, okay? So let me show you a video, and then maybe I can show you, see if this works. So,
and we're back in third quarter planning. Adams is quarterbacking this project.
Sorry about that. Okay, so what we're seeing here is the evolution, like actually the WGAN, in which you see the orange one is the distribution I'm trying to find, and the blue one is the distribution that that the generator is producing. And what we actually see here is on the right is the discriminator, which, you know, in this case is actually you know, giving higher values. So here is going to give higher values to the left, and then the evolution of my generation is going to go to the left because it tries to exploit that, and it's going to go back and forward over and over again, okay? And I have an infinite thing, and this is actually never going to converge, okay? So I saw that, and I was like, okay, and you can see kind of this thing here. So yeah, so you can see like here the generator is on the left. So then this guy has a high on the left. So it takes a while to go, the generator goes towards the left, and then it starts moving back around, okay? So when I saw this, okay, so what's going to happen is these dynamics are going to have some time periodic solutions. And what we are going to be seeing is you're converting to some time periodic solutions. Okay, so what I tried to find was some actually super simple time periodic solutions. And so I simplified everything. So if you take a limit of sigmoids, you can think of it as a step function. And so you can think of the step function of being -1 if z is less than theta, 1 if z is bigger than theta. And then my discriminator is just like a 1 Lipschitz function, W of x plus. And so in this particular example, you can calculate everything explicitly, okay? And you can calculate the d1 distance, which is going to be 1/2 minus the cumulative distribution of theta, okay? So this is with respect of the Gaussian. And this is kind of a useful thing. So if you take a gradient flow with respect of this theta would converge to 0, which should be the one that you're trying to find. But you're not going to be able to train omega fast enough. And so what this algorithm is going to do, you can actually show that the trajectories of this ODE are going to be is going to give rise to periodic orbits. These periodic orbits are contained within the level sets of this energy E of gamma. So if I know the E of gamma at the initial condition, I know what the E of gamma is going to be for all times. And the picture that you are going to have is the following, okay? So here I have theta and here I have omega. So if I start at any point over here, my trajectory is going to keep going through this guy. Okay, so I should think that theta equals to 0 is what I'm trying to see. And so this trajectory is going to go this way until it hits the condition that omega has to be less than 1. And here I got stuck, and then the trajectory goes this way until it hits tangentially this limiting trajectory, which is the red one. And I'm just going to loop in this red trajectory forever, okay? And that's what happens kind of typically, okay? So if you're inside, of course, if you started here, then this guy is going to do the same thing. And okay, and so the only thing that you have is, in a sense, the relative velocity of how fast you're training your discriminator with respect of your generator. So if gamma is equal to 1, this is the picture that you get. But if gamma, okay, sorry, if gamma is equal to 10, what is going to happen is that your limit trajectory takes shorter excursions with respect to gamma equals to 0, okay? So this guy is always going to turn around. So again, if you start here, so if you start at some point here, so what's going to happen is you're going to hit 1 here, then you're going to go into the limiting trajectory, and then you're going to be in the limiting trajectory forever. Okay, and in essence, the idea is that the larger this gamma is going to actually contract your limiting trajectory. But this failure to converge that people have been seeing is also related to the fact that it depends on which kind of orbit you're going to be caught. Okay, so once, and in fact, I mean, that's kind of an interesting problem that yeah, I mean, it's hard enough to even like kind of pose it. It's like how, if you have basing of attractions of these limiting trajectories, and can I find one limiting trajectory that in fact is the one that I'm trying to find? But no matter what, if you haven't taken gamma to infinity, you will always oscillate, okay? And you can get caught, depending on the size of gamma, you can get caught in some trajectory that has some wide motion, with respect of theta, okay? So I want to find theta equals to 0, okay? So my objective is theta star, which is equal to 0, okay? So the farther I'm from theta is equal to 0, the worse I am, okay? And I think I kind of ran out of time. So I guess, yeah, thank you for your attention. And yeah, let me know if you have any questions.
Thank you, Matias.
Thanks.
Any questions?
Yes, I have a question. Hello. Can anyone hear me?
Yes.
Yeah. So if you go back to I don't know if I missed it, but could you perhaps give some intuition as to why in your theorem the constant behaves so terribly in time?
Yeah. So it has to do with the Lipschitz norm of this guy. So the idea is, okay, so, all right, so let me think. So it should be, so it's like sort of this B of theta. So this B of theta is depending on theta itself. So so the idea is that this behaves like sort of norm of theta. So it's not something that when I take the yeah, how can I say it? So when I take the B prime of theta and I try to evaluate it, so when I take the B prime of theta, so the Lipschitz norm, I cannot say that this is less or equal than a constant. I can say that this is less or equal than sort of theta itself. And so then I have to take into consideration that if I'm growing, if I'm growing, then I'm growing faster. And so now the constant is depending basically to e to the Lipschitz norm of v. But now the Lipschitz norm depends on the growth of v itself. And yeah, and the other thing is I also know that b of theta is sort of less or equal than theta itself. Okay, so the size of theta is also going to be growing like exponentially. And so you have to kind of tame both of these things. Does that make sense?
Yes, I see. Thank you.
Sure.
Any other questions? Okay, well, it was very interesting, but of course, it's very different also. So maybe that's why we don't have questions. Thank you very much, Matias.
Thank you. Thank you for